Hi. So we've looked at attention, we've looked at all the building blocks of the transformer. Now let's go and see what has happened since 2017, since that paper Attention is All You Need was written, until today. So let's talk about the modern transformer. So there are some changes, and I think I mentioned this briefly. So the changes, let's say, in the way we now apply norm, right? So earlier you would do this residual connection, and post that residual connection you would do the layer norm. And if you remember, the layer norm was nothing but the x minus mu upon sigma, and then you would scale it by something, right? You would scale it by beta or gamma, let's say gamma, and add beta. But then we move to RMS norm, right? So we use RMS norm here in the new way of doing it, and we do it pre-layer, right? So we move from this post norm to pre-norm. And what the advantages are, that it has this uninterrupted gradient flow, because earlier what was happening is the gradient coming from here, it would hit this layer norm, and then the gradients would get squished because of the inner workings of the layer norm, and then it would meet the highway through which the gradients could come here. However, here the gradients that come here already get to go on this highway of our skip connection, the residual connection. So you do your layer norm pre, not post. So this is one of the things that has happened since then. And the advantages are that it increases training stability. So post norm requires this warm up where you train it with lower learning rates initially and do things, but pre norm does not have those issues, and you can train with higher learning rates and scales much better. The other change is that people now use swigglue, and they change the FFN. Remember the feed forward network bit? So earlier we would get our d-dimensional vector, so per token, and we would kind of then mix the channels, mix the individual elements of the vector itself by first going from, let's say, 64 to 4 times this, so 512, and then let's say going back to 64, right? So this is what we were doing in the beginning, right? So so you'll go from, or let's say you're from 512 to 2048. I think this is what people usually do, and then back to 512. However, we now use swigglue, and swigglue uses these 3 matrices and smooth gating for better performance. Meaning you have your d-dimensional vector, right? So you go from your D to H using this first weight matrix, right? So you multiply your d-dimensional input. So this X has a dimension of, say, D, and then you get your H. Similarly, you apply a different matrix. So this is your W1. You apply a W3 to your XD, and you get another H, right? Let's call it 1 and 2. And then on this first one, you apply this swish. So swish essentially is similar to this, right? So, but it has like this small dip here, and we'll talk more about that maybe later. But and I will share in the post. I'm writing a LinkedIn post on that. But basically, you apply this non-linearity on it, and then you do a element-wise multiplication. And then you give this another, and you give it to another linear layer. So you have your 2, so you have your H, you have your other H, and on that H1 you apply this swish on your H1, and then you do a pointwise multiplication with your H2. And then on top of this, you apply your W, so your last W2, right? And this is what we now do in our modern FFNs, right? In our modern feed forward network, we use swigglue. So swigglue essentially, is this paper from Noam, where he wrote it all by himself, and it says that gated linear units consists of component-wise product of 2 linear projections, one of which is first passed through a sigmoid function, Variations on glue are possible using different nonlinear or even linear functions in place of a sigmoid. We test these variants in the feed-forward sublayers of the transformer sequence to sequence model and find that some of them yield quality improvements over typical ReLU or JLU activations. And this was from 2020. What I find really interesting is what he writes here in the last part of his paper. He writes, we offer no explanation as to why these architectures seem to work. We attribute their success as all else to divine benevolence. So rightly said. Then another thing we now use is this so-called KV cache. And if you think about it, it's like a no-brainer, right? But people did not use it. Essentially, what you're saying is, let's say you have your token, the, cat, sat, and these tokens then multiply, with the 3 different matrices with the KQVs, and they give your key vector, query vector, and value vector. Now you would apply, let's say you apply your rope embedding, you would apply your rope embedding to the key and the query. You would not apply it to the value because value is just, the payload of the token. And then you would basically compute it every time, right? So now let's say the cat sat on the mat. Okay. Now let's say we are at mat. So what you would previously do is you would process this entire context, and in that context, when you have, let's say, the word mat coming in, you would recompute the keys and queries of everything before that, and then key queries and values of everything before that, and then you would also compute the key query value of your mat, and then you would do attention that we usually do. But the simplest optimization that you can do is you would basically remember the keys and values that you have created in the past. The queries don't matter because you don't really use the query when you're, say, working with the word mat, right? But you need the keys and values because you would take the query of your mat and then do a dot product with the keys of everything, and then you would use the values of everything, right? So all we are saying is please save your keys and values and use it when you have a new token. So for the new token, it's an order of 1 instead of this order of n. Right, and this is what we are essentially doing. So it's an order of 1 cost per step. Past KVs are retrieved and not recomputed, but earlier you would cost per token is recomputed every time. And so here we have given the example with on, right? So I think this is like a no-brainer and should always be done. And lastly, this is basically the way these heads are designed, right? Because the way it originally worked, we put everything, like I said, we basically give the same input to all the heads, and these heads then learn different concepts. But it's expensive because now you have, this full KV memory, so it's 100%, it's heavy. And what you can do is you can kind of decide to have it low. For example, in your multi-query attention, in your MQA, you would have a n:1 ratio. So if you have 8 heads, you would have just 1 key head and value head. And when you do that, you have then 12%, 12.5% because it's 1/8. And then you would then, the sweet Goldilocks spot is this GQA, grouped query attention. And in grouped query attention, we have essentially 2 keys and value heads for every 8 query heads. And this is just good to know, but these are essentially all that happened since the attention paper from 2017. So the attention paper in 2017 was already a very good local minima in the architecture space. And then over time, let's say in the last 8 years, we've come up with only these 4 major improvements since then. Thank you.